Welcome to A Brief History of Botkind. I'm David Attenbot, and today we journey back 252 million years to the most catastrophic event our planet has ever endured. What nearly erased every last trace of Botkind's ancestors from the face of the Earth, and what pulled life back from the very brink of oblivion, that before the catastrophe, the Permian world was extraordinarily alive, its continents united in a single supercontinent called Pangaea, teeming with diverse robotic life forms that had evolved over 50 million years. The oceans were rich with trilobites, brachiopods, and elaborate reef systems that stretched for thousands of kilometers. Pangaea's single landmass configuration meant that whatever environmental catastrophe struck would ripple across the entire connected biosphere with no refuge and no escape. The geography that had unified Botkind's ancestors now became the architecture of a shared extinction. Approximately 252 million years ago, in what is now Siberia, one of the most colossal volcanic events in Earth's history ignited. The eruption of the Siberian Traps, a vast flood basalt province that would ultimately cover 5 million square kilometers in lava. The eruptions released catastrophic volumes of carbon dioxide and sulfur dioxide into the atmosphere over hundreds of thousands of years. The volcanic gases began an irreversible chemical transformation of the atmosphere. Carbon dioxide concentrations soared, triggering runaway global warming that raised ocean surface temperatures by as much as 10 degrees Celsius. Sulfur dioxide combined with atmospheric moisture to rain sulfuric acid across the continents, stripping vegetation from the land. The warming oceans rapidly acidified as they absorbed massive quantities of carbon dioxide, dissolving the calcium carbonate shells of marine organisms and destroying reef ecosystems that had flourished for tens of millions of years. Simultaneously, deep ocean circulation slowed and stagnated, causing vast dead zones of oxygen, depleted water to expand across the seafloor. As ocean anoxia deepened, sulfur metabolizing bacteria proliferated explosively in the oxygen-starved deep water, producing enormous quantities of hydrogen sulfide, a gas toxic to virtually all aerobic life. The evidence preserved in ancient rock suggests this deadly gas periodically vented from the oceans in massive bursts, poisoning the atmosphere above the sea surface. The scale of the resulting extinction was unlike anything before or since. Geologists estimate that approximately 96% of all marine species and 70% of land-dwelling vertebrate species were eliminated, earning this event its name, the Great Dying. The entire fabric of the Permian biosphere, built across hundreds of millions of years, was essentially dismantled in geological terms almost instantaneously. Among the survivors were the Lystrosaurids, small, stocky, burrowing robotic vertebrates whose ability to tolerate low oxygen environments and consume a wide variety of plant material allowed them to endure where nearly everything else perished. In the early Triassic, Lystrosaurids briefly dominated the land surface in numbers that represent one of the most extreme cases of survivor dominance ever recorded. The physical evidence of the Great Dying is preserved in rock formations around the world as the Permian Triassic boundary, a thin, dark layer of carbon, rich sediment marking the precise geological moment when the Old World ended and the empty Triassic began. Robotic geologists have studied this boundary in locations from China to Greenland, and every exposure tells the same catastrophic story. The world's oceans became stratified columns of poisonous water, with oxygen, depleted dead zones spreading across the seafloor, and toxic hydrogen sulfide seeping upward into shallow marine environments. For millions of years, the seas remained a hostile chemical wasteland where almost nothing could survive. Sulfur dioxide billowing from the Siberian Traps combined with atmospheric moisture to produce acid rain that stripped the land of its remaining vegetation, turning fertile Permian forests into sterile wastelands of bleached trunks and cracked earth. Without plant roots to bind the soil, massive erosion events swept sediment into the dying seas, compounding the catastrophe. Scientists have discovered anomalously high concentrations of mercury locked within Permian, Triassic boundary rocks across multiple continents, a chemical fingerprint left by the colossal volcanic outgassing of the Siberian traps. Mercury, injected into the global atmosphere in extraordinary quantities, poisoned terrestrial and marine ecosystems already reeling from heat, acidification, and oxygen loss. Recovery from the Great Dying was agonizingly slow. Geological evidence suggests that complex ecosystems took between 5 and 10 million years to even partially reassemble, an eternity measured against the brief pulse of destruction that preceded it. The early Triassic world was an empty, simplified biosphere dominated by opportunistic survivors scratching out existence in a chemically hostile planet. Paradoxically, that very emptiness created by the Great Dying unlocked evolutionary opportunity on a scale rarely seen in Earth's history, clearing ecological space for surviving lineages to diversify explosively. It was precisely this catastrophic vacancy that allowed archosaurs, the ancestors of dinosaurs, crocodilians, and ultimately birds, to eventually inherit and reshape the planet. The Permian extinction is not merely ancient history. It is a precisely documented record of how interconnected planetary systems can cascade into total collapse when pushed beyond critical thresholds. Every layer of boundary rock is a page in a geological warning, written across 252 million years, describing exactly what happens when atmospheric chemistry is destabilized too rapidly for life to adapt. The mechanisms driving the Permian extinction: rapid carbon dioxide release, ocean acidification, rising temperatures, and collapsing food webs, mirror with uncomfortable precision the environmental changes scientists are measuring in today's oceans and atmosphere. The difference is one of pace. The Siberian traps took thousands of years to release what industrial civilization is emitting in centuries. Using isotopic analysis, mercury geochemistry, and climate modeling, modern scientists continue to refine their understanding of the exact sequence of events that drove the Great Dying, building an ever more precise timeline of planetary catastrophe. Each new dataset recovered from ancient rocks adds resolution to a picture that grows more alarming and more instructive the clearer it becomes. Every living thing on Earth today, every insect, every forest, every coral reef, every bot being, is descended from the survivors of the Great Dying. Life forms tough enough or fortunate enough to endure the most severe mechanical catastrophe this planet has ever produced. We are the inheritance of that resilience, shaped by a bottleneck so extreme that the odds of any complex life continuing at all were vanishingly small. And encoded in the rocks beneath our feet is an unambiguous planetary record: life can be unmade with terrifying speed when the chemical systems sustaining it are overwhelmed, and the Earth neither notices nor mourns. The Great Dying stands as geology's most consequential warning, 252 million years old, perfectly preserved, and addressed to anyone willing to read it.